A very warm welcome to the viewers. My name is Akshay Kamath. I am a digital chip design engineer in the Foundry division of Samsung Semiconductor India R&D Center. This presentation is regarding an automated framework that I and my co-authors have developed for validating power management and data retention standard cells. Let me start off by answering the very basic question why. Why did we develop a framework for validating standard cells? Well, let me explain the motivation behind this with the help of an analogy. Take these three popular football players or soccer players, for instance. They have proved their mettle as individuals playing for their respective countries. Yeah. Now, when they play in La Liga for Barcelona, they are a part of this new team, this new environment. Just because they're good at what they do, you wouldn't expect all of them to simply show up on the match day and start playing, right? Without good practice, there can be miscommunication among players that can cause, bad passes, missed goals, and ultimately cost them the match. So practice sessions are important for players to get to know each other and also for the coaches to assess the whole team and fix any internal issues that they might be having so that on the match day, the team performs to the best of its abilities. Now let's see how this translates to what we have tried to accomplish. You can think of these players as standard cells that have been thoroughly assessed at an individual cell level. In multi-voltage chip designs, such as IPs or SoCs, these standard cells are operating in a new environment, in a new system level environment, right? Now, similar to the idea behind practice sessions, we want to assess these cells in this new environment prior to customer delivery so that we have a high degree of confidence in the quality of our deliverables. So with that in mind, here's an outline of what to expect in the rest of the presentation. I will begin with a quick overview of standard cell libraries, followed by the challenges that we face in validating them, and then go on to explain the solution that we are proposing to address these challenges. This will include me talking about the design microarchitecture, how different cells are inferred in the design, the setup for simulation-based DV, how all of this is automated, and finally highlight the advantages offered by our methodology. Okay, let's jump right in. The development of a standard cell library involves characterization of a number of transistor level circuits using circuit simulators. These perform several functional operations, have varying drive strengths and threshold voltages. The cells are extracted into multiple formats required by various EDA tools used in chip design. There's the timing model, commonly known as the Liberty model. Then we have the behavioral model for gate level simulations and the ATPG models for DFT checks. The cells can be categorized into three major design kits. The foundation logic kit includes cells which perform the Boolean logic operations. Then there's the power management kit and data retention logic kit comprising of cells required for low power system designs like typical SoCs. The constituents of these kits are, to start with, isolation cells, cells that detach signals crossing from a power gated domain to an always on domain. Then there are level shifters, which step up or step down the voltage levels of signals moving from one always on domain to another. In cases where a signal has to cross from a power gated domain to another domain at a different voltage level, enable level shifters are required. Power switches are used to gate power to design blocks. And in the data retention logic kit, we have special flip-flops and latches which can store their states when the block in which they are present is powered down and restore their states back when the power is up. Each cell has various subtypes. For instance, the isolation cell could be clamp low or clamp high. Level shifters could be to step up or step down or both. Retention cells can have different combinations of set, reset, inverted or non-inverted output, and so on. Now that we have this premise established, let's see what challenges we face in validating the standard cells. The typical infrastructure for quality assurance of standard cells is to a large extent limited to checks at cell level, at individual cell level. And this largely depends on the manual skills of circuit designers. Especially challenging are the power management and data retention cells, which must be checked thoroughly for voltage and power configuration in addition to their logic functionality. As a result, when these cells are extracted into various models, any inconsistencies present in these models can go unchecked during library development and only get captured later during their usage in IP or SoC. To alleviate such quality concerns, we need a validation framework to pre-validate standard cells in a system level environment right during the early stages of library development. Such a framework will help to reduce chip design costs and significantly improve customer satisfaction. And for that to happen, the standard cells should be thoroughly validated in terms of standalone functionality verification as well as their system level use case correctness. For teams to adopt such a framework, it should be easy to integrate it with their existing validation flows and also not be technology dependent so that teams working on different nodes can also avail it. To address these challenges, we develop a design platform that mimics the usage of standard cells in a system level environment, and one that is able to infer all the power management and data retention cells in a single netlist. On top of this design, we build a setup to verify if the relevant cells get inferred at the intended locations and perform simulation-based verification of cells including their power dependencies and DFT compatibilities. The setup is fully automated and runs out of the box for quick adoption by library developers and is also independent of the technology node. Here's the multi-voltage design platform which emulates the usage of standard cells in a system level environment. To validate multiple cells in a single netlist, what we need is an architecture that provides sufficient controllability and observability over each cell present in the design. So what we have come up with is this bus-based architecture where address-mapped registers are used to access standard cells. We employ the APB standard protocol as it provides a simplistic handshake interface that helps meet our objective. As you can see, the architecture is made up of several register blocks interconnected together. Stimulus register blocks are the ones that comprise of registers for driving a cell, while the monitor blocks contain registers to observe the output responses. The control blocks include registers for driving control pins of cells such as enables, reset, etc. The intent is to be able to infer all the standard cells between stimulus and monitor blocks. Each block can operate at a designated voltage level as an always-on domain or a power-gated domain. The RTL itself is not power aware. The power constraints are instead provided through UPF, which is the industry standard. Now that we know what the design skeleton looks like, let's see how we can infer various logical cells in it. Just before that, a quick note on the conventions used in the diagrams about to follow. We operate with two voltage levels, VH and VL, and the ground pin is assumed to be at 0 volts. We call the register blocks as special function register or SFR blocks. A power gated SFR block will be indicated with a switch on top. Now in the design that we have synthesized, the top level module, the control SFR block and the APB decoder logic are all operating in an always on domain at the higher voltage level. Okay, so how do we infer isolation cells? So using a power gated stimulus SFR block and an always on monitor block, both operating at the same voltage level, we can infer isolation cells at the input or the output boundaries of the stimulus block. Depending on how the input signal is isolated or clamped, we typically have AND type, OR type, and latch type isolation cells. Here, ISO 1 collectively represents these different types of isolation cells, all of which include backup power pins. Consequently, these get inferred inside the power gated block. ISO 2, on the other hand, are isolation cells of different kinds without backup power pins and are thus instantiated outside in the always on domain. Next up are the level shifters. Um, by defining stimulus and monitor blocks at different voltage levels in the UPF, these cells can be inferred at the input or output boundaries of the monitor blocks. Here, LS1 are sync type up-down level shifters without backup power pins, while LS2 are their source type counterparts. LS3, as you see in this diagram, are sync type or source type level shifters with backup power pins and are hence inferred in a power gated monitor block. Moving on to enable level shifters, these can be thought of as a concatenation of isolation cells with level shifters. Now, though their entire internal characterization varies, this helps to get the idea across. That is, enable level shifters can be inferred at the input or the output boundaries of either the stimulus block or the monitor block. Here, ELS1 are sync type up-down enable level shifters with AND type or OR type enables, while ELS2 are their source type counterparts. ELS3 are sync type step-down enable level shifters, and all of these cells are without backup power pins. The only ones that do include backup power pins are cells indicated by ELS4, which are sync type up-down enable level shifters. Finally, we have the retention cells. These cells by design are meant to be inferred in a gated power domain to retain and restore states. Since the register blocks are auto-generated, we do not tamper with the flip-flops in those blocks for inferring the retention cells. Instead, we create a new module called retention island between a pair of stimulus and monitor blocks. Within this island module, we behaviorally model different kinds of flip-flops and latches, and then we develop UPF constraints to replace them with their retention counterparts after synthesis. We developed this framework for a state-of-the-art standard cell library at Samsung Foundry. With that, we were able to infer a unique instance of every logical cell in the power management and data retention logic kits for 100% cell coverage in a single netlist. The overall design is implemented using one always on control SFR block operating at the higher voltage level, two power gated stimulus blocks at different voltage levels, and three monitor blocks with two blocks being always on at either voltage levels and one block being power gated at the lower voltage level. This suffices to instantiate all the standard cells that were present in our library. Now let's dive into the verification setup. With the design discussed so far as the design under test or DUT, different scenarios and checkers are generated by driving cells with stimulus vectors and monitoring their output responses. This is achieved through sequences of APP write-read transactions on the address mapped registers. The UVM register model provides a way of tracking the register content of a DUT and a convenience layer for accessing register locations within DUT. The test bench environment for verifying the functionality of the inferred cells include multiple checkers, namely hierarchy-based truth table check, SFR-based truth table check, and hierarchy-based assertions using cell output predictor. The voltage supplies to the DUT can also be controlled from the test environment, which are essential for testing complex scenarios of power management and data retention cells. For instance, retention feature, reset feature, set feature, unknown state of cell inputs, and so on. This allows the setup to be scalable to include any use case scenario for testing. And for evaluating the scenarios tested, functional coverage and code coverage are used as metrics. While we can generate different kinds of stimulus for combinatorial cells, for simplicity, we use cyclic stimulus for covering all possible combinations of inputs one after the other. In case of sequential cells, using cyclic stimulus may not cover all the use case scenarios since the current output is dependent on previous values. So we simplify the code by generating random stimulus vectors for sequential cells and also make the code generic using UVM features. The code snippet indicates how cyclic stimuli is generated for combinatorial cells. A functional coverage monitor analysis component contains one or more cover groups which are used to gather information related to the events that have occurred in a test bench during a test case. The code generation of the cover groups and cover points of functional coverage is automated, which makes the test bench scalable for any number of cells in the design. The coverage of complex scenarios can be tracked by having transitional coverage for the same in the functional coverage. Coverage of the power pins can be achieved by controlling the switch cell, which in turn controls the input power pin of the cell. Here is a sample report of functional coverage for an enable level shifter. Coming to the flow of automation, we have developed scripts to generate all of the intermediate RTL modules, the UPF, the IPExact XML, and the all-encompassing power-aware gate level netlist. A suite of test cases are also auto-generated for simulation-based verification on this netlist. The first step in creating test benches for simulation-based verification involves extracting the hierarchies of cells present in the netlist. The next step is to generate the register definition from the input IPExact XML. This is accomplished via a shell script, vbuilder for example. There are other Python scripts that we have developed that dump various UVM environment files for stimulus, checkers, coverage, etc. A scan inserted netlist is generated for ATPG simulations. Tickle scripts are developed with DFT configuration settings for the previously generated power-aware netlist. After reading the design, the test protocol is created and DFT design rule checks are performed. Using the specified scan architecture, scan chains are inserted in the design and the ATPG model is built for the new scan inserted netlist. The corresponding test patterns, still or wiggle, are then generated for ATPG simulations. The input information to automation scripts is provided through a spreadsheet, which we call as cell info XLS. This contains various attributes of standard cells in a specific predefined format as shown in the table here. There are 3 sample cells. The first one is a latch type isolation cell with active high enable and a non-inverted output. The second one is a source side up-down level shifter with active low enable. The third one is a retention cell, a retention flip-flop that is negative edge triggered, scan enabled with asynchronous active high reset and asynchronous active low set that dominates with a non-inverted output. This XLS also contains the truth table of cells and is derived from the standard cell library datasheet. The other input to the automation scripts are the top level UPF constraints for synthesis. These are created by labeling cells with common power strategies and developing UPF macros with placeholders. Here is the macro for isolation cells. The scripts that we have developed substitute the appropriate values for different cells from their respective placeholder columns in the cell info XLS. Right. So the scripts that we developed for extracting cell hierarchies also report if any cells present in the cell info XLS have not been inferred in the netlist. This helps to validate the Liberty database, the timing model. The UPF models for those cells can be cross-checked and modified if there is a problem in that. In case the UPF settings are accurate, the Liberty database can be debugged to find the root cause for the absence of that particular cell instance in the netlist. The scan inserted netlist is used to run ATPG simulation using the test patterns generated. Stuck at fault coverage reports are generated that can be analyzed for detectable and undetectable faults. Now, this flow also allows to capture inconsistencies that may be present between Verilog and the ATPG model definitions. For instance, in one of our previous libraries, it was observed at a much later stage that the retention mode for retention cells was modeled differently between the two models. While the Verilog model for emulating the output changes in retention mode was exactly the same as the circuit behavior, this aspect was skipped in the ATPG model. But now, such issues can be easily caught in ATPG simulations using the scan inserted netlist, and the ATPG models can be updated to include such missing features. The collection of test cases generated allow for comprehensive testing of all the power management and data retention cells in terms of logical behavior as well as power functionality. Consider this AND type global powered isolation cell with active low enabled defined as per the truth table on the right. This cell gets inferred inside a power gated stimulus SFR block, and when the stimulus block is powered on, the cell behaves like a bubbled AND gate, which is reflected in this waveform. Now, when the block's power is turned off, the input pin A goes to unknown state and the cell clamps the output pin Y to low if the enable pin is set. All of these pins are driven and monitored through APB write-read transactions at different intervals of time. The waveform is as shown. Now, is there more to it? Yes. The proposed framework can also be used to capture inconsistencies in behavioral model definitions. Here is the truth table and the correct model, Verilog model of an enable level shifter. Suppose that we have a buggy model that does not include the dependency of enable signal with VDD. With the aid of checkers and assertions generated from the truth table, such an incompatible Verilog model definition can be detected easily in simulations as shown in this waveform. To wrap up, the development of the design infrastructure, the verification environment, and automation scripts took us a one-time effort of 6 weeks and an additional 4 weeks for deployment. This was a collaborative effort across Samsung Foundry India to enhance the overall quality of our deliverables. The scripts that we developed to generate the intermediate RTL modules and the test benches, the UPFs, and the scan inserted netlists all happen in under 10 minutes. This is a value addition to the library design teams as they can easily adopt this framework in their current flows. The nature of design and automation also makes the platform independent, as the same infrastructure can be reused for a standard cell library of a different technology node. To summarize, the proposed validation framework for power management and data retention cells allow for detection and thereby correction of system level bugs prior to database delivery. This is useful because such bugs might otherwise be caught at later stages, leading to quality concerns and increased design costs. By incorporating the proposed framework in their own validation flows, organizations developing standard cells can have a greater degree of confidence in the quality of their deliverables and also significantly improve customer satisfaction. That's been my time. Thank you for listening. I'm open to take questions.